because they are not make me. Yeah, okay, now they make the co-host. Yes. So here, due to the mutual influence, the splitting of signal is takes place, and that in the splitted signal, okay, in the splitted signal, so the separation of that signal, okay, the gap between that signal is indicated with the J value. J is a coupling constant. Okay, J is a coupling constant. For example, you can see, right? So here, one signal is splitting like this. Okay, so now the gap between this here. Okay, so here the gap, this signal to this signal, the gap here, right? And here the gap between these two signals here. It is indicated with J value. Okay, so J, this is also the units for this J. J nothing but the coupling constant. Okay, and delta is a chemical shift values. Delta is a chemical shift values. For this chemical shift also the units are heads here. Okay, heads here. And J for J coupling constant also the units are heads. Okay, and here the coupling constant, right? The coupling constant nothing but the separation of signals. The separation of signals is called the coupling constant. The gap between the signals. For example, triplet is there, right? Or the doublet, you can say, right? Here in the doublet, two lines are there. So how much gap is there? How much distance is there between these two lines? That is called the coupling constant. Okay. So now you can see the, for example, here groups are given like CS3, CS2, CS2, CS3. Okay, so here this is the N-butane, right? So in the N-butane, where it is symmetrical compound, so you get two signals here, right? You will get two signals for this N-butane, and the coupling constant here, right? The gap between this signal is okay J to HH. Okay, the two means the intervening bond. The two nothing but intervening bonds. So intervening bond means the adjacent one C. Okay, so right here CH. Okay, here is CH for example. Again, here is CH. Okay, so if the right, so this is the distance. We call this is J. Right, this is adjacent 1, 2, 3. Okay, so the gap, or you can say the coupling constant between the C1 carbon and C2 carbon. Right, it's only the two carbon separation here. Right, you have the two carbon separation. So J2. For example, if this proton, right, C1 proton is coupled with this proton, C3 proton, then we call it is J3. We indicate with the J3. So intervening bonds, 1, 2. There are, right, here is 1, 2, 3. There are three intervening bonds are there. Okay, three intervening bonds. So like that. So there are three, means J3. Okay, so here in this particular N-butane, we have this J2, HH. HH means generally the coupling between the, it is homonuclear coupling only. In the proton NMR, you can see only the homonuclear coupling. No heteronuclear coupling is observed in the H1 NMR spectra. You can see the heteronuclear coupling in the with the C13 spectra here, right? Because there are carbon and hydrogen coupling will be takes place here. Okay, C13 coupled spectra and decoupled spectra is there in C13. So there are two types of spectra, coupled spectra and decoupled spectra. But here, where the homonuclear coupled spectra only, homonuclear coupled spectra. So the J value, it is 1.6 here, and again J3. Okay, here J2HH is 1.6 and J3HH. J3 means 1,3 carbon. Okay, the proton, the distance, the first C1 proton and C3 proton here. C1 proton and C3 proton. The J value, it is 7.2, and C4 proton. Okay, when the coupling is with the 5. Okay, C1 and C4 proton, then it is the value 0.3. Okay, so that is the distance between these protons. And generally, you can see in the homonuclear coupling, we can observe the coupling constant up to means 3 intervening bonds. Up to 3 intervening bonds is allowed. The coupling is allowed up to 3 intervening bonds. Beyond that, you can see very weak interaction. Very weak interaction is takes place here. The coupling is not possible. If possible, it is very weak interaction. Will get only there is weak bands or weak peaks are observed here. Okay. And all these are the how to calculate the multiplicity. How to okay. So you can see the multiplicity here. So you can see here the pi n plus 1 rule, right? That multiplicity is obtained, and the intensity of this multiplicity. For example, if you get the trip doublet here, so what is the height of that? Okay, height of that particular two lines in the doublet, and triplets. What is the intensity of that triplet signals? So you can see in this Pascal scale okay, diagram here. Okay, so generally that intensity will be calculated by A plus P whole square formula generally. Okay, so we'll follow the A plus P N, or not whole square here, A plus P N here. So A plus B. Yeah.
Sir, good afternoon.
Yes, good afternoon.
Sir, one in the open that page, last one, sir, the value J4.
Yeah.
J4.
Yeah, J4. 1,4. That the coupling between 1 and 4 carbon. Right? Here,
yes. Last value, sir, J4. That H1.
J4, yes. How much it is? 0.3. Isn't it? This one?
Sir, the figure had been made, sir. About that I'm asking.
Figure? Okay, last one. This one, huh?
Yes, sir.
Okay, 1.5, huh?
Yes.
Yes, 1.5. So here, the intervening bonds here. This is 1, 2, 3, 4. Got it? Yeah, that 4 intervening bonds here. Okay, so in 4 intervening, the gap here. This is 1 here. This is 2. This is 3. This is 4. Right? So there are 4 intervening bonds are there. And the value, right? The gap means the coupling constant value is 1.5. Okay. And here you can see some where is the right the up downs in the values here. So this is only due to some factors, you know that, right? So here you say this is nor-borne in here. This is nor-borne in structure. So in the nor-borne structure, it is bridged compound. So due to this, some right, the steric factors will be applied in this case. So we are getting the value fluctuation in the values here. Okay.
Sir, your upper line is showing as a non-bonding protons.
Yes, that is unsaturated one, no? Upper one is unsaturated one. So that is I am telling what I am telling is here the factors are here is a if you see in the saturated one, okay, here in the saturated one, so where the for J4 it is 0.3. So in the unsaturated one, okay, J5 value here it is 1, 2, 3, 4, 5. Okay, so this is the butadiene, right? You can see butadiene. So
Yes.
here the J5 value, it is 1.3.
Sure.
Right? So because there are electronegativity increases now, right? So
Yes.
electronegativity increases and it is pi bond. So you know that the pi orbitals are in the parallelly oriented here. In the sigma orbitals are in the right. So it is oriented perpendicularly. So
Yes.
some factors are there. So the values is the J values are the delta values uh, will be obtained based on the factors here. So many influencing factors are there, as we discussed in the class, right? In the IR spectra, in the UV spectra also we discussed some solvent effect will be there, right? Electronic factors and steric factors, hydrogen bonding factors here. Okay, and inductive effect, mesomeric effect. So all these are the factors they are influencing they affecting that delta values here. So only thing
Yes.
is just
Yes.
J.
Thank
What
you,
is
sir.
J here? Yes, from right. So the J nothing but your coupling constant here. Coupling constant definition is where the separation of the signal is coupling constant. That's all. And here you see the getting of the multiplicity intensity. Simply we follow the right. So a plus b power of n, that is formula here, right? So in the a plus b power of n here, the for example, if you get okay, according n plus one rule, okay, n plus one rule, if you get one, so n you take one, right? So n power a plus b power of one, then you get a plus b power of one means you get only one each table. So it is 1:1 here. Okay. So for singlet, generally, it is only one signal. So no comparison between the signal intensities here. And for doublets, okay, for doublets, where the n equal to 1 here. So you can see the intensity 1, A equal to 1, B equal to 1. So it is, okay, in the doublet, A equal to 1, B equal to 1. So we will get, here is a equal intensities here, right? So here the table is given. So if the mass peoples are there, you can more aware of that Pascal triangle. Okay. So Pascal triangle. So how to draw that and what is the consequences of that n values here. So you know that here the n equal to 0, for example, here n equal to 0. When you get the n equal to 0, if there is no neighboring protons here, there is no neighboring proton, then you get the n equal to 0. So a plus b, okay, whole power of n, that equal how much it is? It is 1 only, isn't it? A equal to 1, B, right? So there is no B here. So n power of A equal to 1 only, right? Some x power of 0 equal to 1 only. No? So the mass people will uh, understand betterly here. And if n equal to 1, means when the neighboring proton, one neighboring proton is there, okay, one non-equivalent neighboring proton is there, then we got the A plus B power of 1. So here is A power 1 plus B power 1. A equal to 1 plus 1. Here is 1:1 here. 1:1. So intensity equal. If the doublet is there, okay. So if the signal is split into doublet, so equal intensity here. You can see the equal intensity. So 1:1 here. And if it is triplet, for example, right? So if it is triplet, so when you get the triplet here, actually, so if the neighboring, there are neighboring two non-equivalent protons are there, then we get the triplet here, isn't it? Because 2 plus 1, it is triplet. So A plus B, okay, whole power of 2. Here 2 nothing but the number of non-equivalent protons. Then here is A equal to 1, right? So B equal to 1 here. Okay, so 1 power of n. So what is the formula here? A plus B whole square here. Okay, so A plus B whole square. So you say it is A square plus 2AB plus B square. So A equal to 1 here. 1 square equal to 1 only. 2AB. 2 into 1 into 1. That equal 2. Right? And B square. B equal to 1 here. So 1. 1 is to 2 is to 1. Isn't it? 1 is to 2 is to 1. Okay. So if there are 3 non-equivalent protons, n equal to 3 here, for example, n equal to 3, then it becomes a plus b whole cube, and a plus b whole cube, the formula, means the math people should tell this. So what is the formula? A cube plus 2a square b plus 2b b square a, I think, a b square, okay, plus b cube. Isn't it? Is it correct, MPC people? A plus b whole cube formula. That equal to, I think, it is a cube here plus 2 a square b plus 2 ab square plus 2, plus b cube, I think. So here the a equal to 1 here, isn't it? B equal to 1. So 1 cube, that is 1 only. Okay, a cube, that is 1. 2 a square b. So 2, okay, 2 a square b, how much it is? 2, yes, 2 into 1 square plus 1.
Sir,
Uh,
a plus b cube is equal to a cube plus 3a square b plus 3ab
a square.
square plus b cube.
I don't know. So you tell, because I don't know formula, because I am not belongs to MPC here, maths here. So
Yes,
you
sir.
can go with this. You can calculate. Then you will get this. Okay. So 1 is to 3 is to 3 is to 1 here.
Yes, sir.
Okay. Then you get triplet here. Means here the intensity. Just here, what is this Pascal triangle telling this? The intensity ratios here. If the doublet is there, so the intensity means equal intensity here. Two lines, right? In the multiplicity, the two lines is with equal intensity. If triplet is there, so one here is 1, 2, 3. So where the 1 and 3, these two are with equal intensity, and the middle signal is with the double to the adjacent one. Okay. So the intensity of the middle line is, okay, 2 times than your the adjacent one. And if the 3 non-equivalent protons are there, n equal to 3, then the, okay, you get the quadrate here. So in the quadrate, for showing of that signal intensity, here is 1, here is 3, 1/3, here is 1/3, and 3. So where 1 and 4th lines are same, and 2 and 3 lines are with the same in the height here. Okay, these two are same, these two are same height. Okay, the height of the signal is, here is, these two are same, these two are same. For assigning this, right, the intensity means for assigning this height. So generally we follow this Pascal triangle formula, and the derivation of this Pascal triangle. So generally a plus b, we follow the a plus b power of n formula, and you can substitute in place of n. So 1 and 2, 3, 4, 5, 6. So like that. Based on that, you can derive the formula, and you go with that. So you get whatever you get here. So that is the intensity of that signal height here. For example, here n equal to 4, you get the quadrate here. Sorry, quintet. N equal to 4, n plus 1. So you get the quintet. So in the quintet, you see the first one and the last one. Okay, the first one and last one signal height, line height, not signal. We cannot say signal here, because signal, only one signal is there, and that signal further split into lines, different multiplicity here. Okay, so the this one and this one is with the same height, and this means uh, 1 and 5th is with same height, and 2 and both is same height, and third one is it is more intense than the remaining thing here. Okay, so like that. So the intensity in the means here the painted, right? In the painted, like you how to draw that painted here. So this is here, then this, then like this here, like this, and like this. You can see. So these two are with same in the height. These two are with same height, and this is different. Yeah, more height than this and this. Okay. Yes. So this is the Pascal triangle for us means indicating the intensity of the height of that signals here. Yes. Next, the coupling constant values. So you can see the coupling constant values. General coupling constant nothing but the separation of the signals, right? And values are obtained for these protons with the different types of protons here, like geminal coupling, vicinal coupling. So you know that say geminal coupling means when the two protons are attached on same carbon here. Then we'll observe the geminal coupling, and vicinal coupling you can observe for the
Sir,
adjacent.
excuse me, sir.
Yes.
In Pascal triangle, sir, that n will be 6 only, or it can be
Yeah.
more than 6. It can be more than
N
6.
equal to 6. So
Ji, sir.
septate. You have to septate here, and the
Ji.
intensity is this one. Okay.
Can be more than 6 also, sir.
Okay. In the Pascal triangle, actually, uh, a plus b whole power of 6 here. Then you derive the formula here. I don't know because actually a power
No, sir. I am
a plus b
asking
the
n
power of
can
6
be
means,
in
and
case, sir.
generally for yes, I will tell you.
Sir, my
Actually, here what we do.
sir, my question is n is equal
Hmm.
to maximum 6, or it can be
Not
7.
maximum 6 here. Not maximum 6.
Okay.
Here there is no means maximum 6 means.
Ji,
So
ji,
just we are taken up to 6 here actually.
ji,
There
ji.
is no maximum 6 here. So why
Okay,
you
sir.
are taking 6 is, so more after actually after 5, okay, quintet or the pentate. Generally we take we consider it as a multiplet. Okay,
Sure, sure.
we consider it as a multiplet here.
Ji, sir, ji, sir.
And and one thing is here, if that one signal is undergoes splitting and it gives a multiplet here, means a multiplicity, right? If more than 5 lines are there,
Sir. We
you are
will take as a
we are
multiple.
unable to, okay, we are unable to assign that multiplicity actually, and we will get a very complex signal there,
Sir,
right?
sir.
Because that is unresolved actually, that is very unresolved and very complex what is that signal is obtained,
Ji,
and
sir.
we are unable to right, so unable to discriminate that the height of that one, so we'll get a some kind of clumsy, okay, we'll
Ji,
get a some kind of clumsy signal here. That's
sure,
why
sir.
actually we'll consider up to 5, so we'll get a very neat presentation. After
Ji,
5, we won't get the neat presentation. That's why simply we are giving multiplets. Already
yes,
we have seen in the graph also, right? So in the
sir.
spectral analysis, we done the spectral analysis, and we have seen the graph in the uh, manually, right? So
Sir,
if more than 5 lines are there, so we'll get very clumsy spectra.
sure,
Okay.
sir.
Yes, yes, yes. Second, sir. Okay, so next we are moving to this coupling constant. So for means this coupling constant is depending on that the number of intervening bonds here, and some factors will be influence on that particular coupling constant values. And we'll see how the coupling constant is varies depending on the factors and types of protons here. We can see table. So here's profit constant. And here we see this in this example, speed. Okay, towards cup constant 0 to here. Same thing when it is attached with unsatisfied olefinic bonds. Olefinic general proton values for two. There is in the ethane. Okay, so in the ethane derivative like HA and HB means it is vicinal proton. For the vicinal protons, the vicinal coupling values here, where it is 6 to 8, and in the vicinal in the olefinic protons, the value is 0 to 3. Okay, and in the trans, actually it is in the trans, it is 0 to 3, and in the cis also it is giving 0 to 3 the delta value, and the coupling constant value is it is differing, right? The delta value is this one, and where the coupling constant value is differing, like for trans protons, the J value is 1.5, and for cis protons, means what is this? 1, 2, 3. Yes. So vicinal. Okay. So vicinal trans protons here, so cis protons, the J value is 2. Okay. So by this J value, you can differentiate the cis and trans configuration also. So H1 NMR spectra. So by chemical shift values, you can't differentiate that because both are appears in the same delta values here. But by J value, you can differentiate here. Right? So because you see in the trans where the spatially both the protons are spatially separated here, and in the cis where both the protons are on the same phase, same direction. So the separation is less. So where you can see the different J values for the cis and trans here. Okay, and then here also in the cyclohexane chair conformation, right? The cyclohexane chair conformation, there are different coupling right? What is it? Coupling constants here. Axial and axial. Okay, so in the cyclohexane, right? Cyclohexane derivative chair form, we have the axial bonds and equatorial bonds here, right? And here the coupling is possible between axial and axial, equatorial and equatorial, and axial and equatorial, right? So there are three types of couplings are possible here, and you see axial and axial, right? The delta value is 6 to 14 here, and the coupling constant value is 8 to 10, right? And for axial and equatorial, where the axial means when that orientation the bond, right? Axial means downwards here, okay, and equatorial is that upwards. So axial, one is the upwards, one is the downwards here, right? So in the both configuration is different, right? So the one is to above means upwards, one is downwards. In the axial and equatorial coupling, where the J value is 2 to 3, and equatorial and equatorial also you can found it is 2 to 3 here. Okay, so these are and in the cyclopentane also it is given for the cis and trans configuration, right? For cis and trans configuration, we have the difference of that J value 5 to 10 is 10. Okay, so these are the protons J values here, and it is not means it is not a what is that constant values here, so it will be variable. the value will be variable depending on the some factors. So the value will be some fluctuation will be takes place here. Means sometimes the value will be increases, sometimes the value will be decreases here, right? But these are not the fixed values here, actually, right? So this is a table showing the coupling constant values here. And very important question which can be in exam is uh, spectrum of H1 spectrum of your ethanol, pure and impure. Okay, pure and impure ethanol. This is very important question actually. Right. So, and the graph or the spectra for the H1 NMR spectra for this pure alcohol and impure alcohol. Right. So both will be different. For pure alcohol, let's here the formula is same here. So CS3, CS2, OH. Right. So for if you see the spectra, H1 NMR spectra, this is TMS here, 0. Okay. So you can see there are two, okay, equivalent proton, two non-equivalent protons, right? This is A, this is B, and this is C. Okay. So, for example, just you assume this is the pure alcohol. If you take this as a pure alcohol here, right? So for pure alcohol, okay, for pure alcohol, so the proton, right? The OH proton will be retains in the pure alcohol. You can observe these signals for OH proton also. So it will be coupled with the neighboring proton here, right? So in that way, so for the A type of protons, okay, A set of protons. So what is the multiplicity for A set of proton here? The neighboring adjacent there is two protons here. So 2 plus 1, it is triplets. So you will get the triplet for this. And for the B type of protons, B set of protons, so you will get here is 3 and here is 1. 3 plus 1, 4 and plus 1 here. There are 5. So you will get the quintet. Okay. It is pentet or the quintet here. And for this OH proton, okay, for this OH proton, you will get the triplet because there are adjacent, there are two protons are there. So you will get the triplet. So triplets, quintet, and triplet. So this is the H1 NMR spectrum of, okay, there is a triplet, and quintet here, and again triplet. This is the H1 NMR spectrum of H1 NMR pure alcohol. Pure alcohol. Okay. Here triplet. Here is a quintet and a triplet. This is the NMR spectrum of your pure alcohol. Because in the pure alcohol, there is no exchange of the proton. There is no exchange of OH proton here. So we'll get the multiplicity for OH proton also. And in the means here laboratory ethanol and impure ethanol here given, right? Coupling impure and laboratory. So for laboratory ethanol, we'll get the triplet, quintet, and triplets. And for impure alcohol are the ethanol. So for impure alcohol, where the CH2 and O, right? So for the impure alcohol, so impure alcohol means it is mixed up with some impurities here. So the OH proton will be, right? The OH proton will be reacted with the impurities and it will be replaced here. Okay, it is exchanged with the impurities. So the escaping of OH proton is takes place here. Okay, so there is no proton attached to this OH group. So then what will be the multiplicity for each and every set of protons here? For this, you will get the triplet. For this, you will get the quadret here. And there is no signal for OH proton. So you will get the only two signals with the triplet. Okay, and the quadret. Okay, so this is the H1 NMR spectrum of your impure alcohol. Okay, So for pure alcohol, you can see the three signals. For impure alcohol, you can see the two signals only. So this is very important question which can be expected in the examination. Or if you go to any industry interview here, in industry interview or any CSR interview or anywhere you go. So actually, or you go if you go
Sir, excuse
for the
me.
faculty, yes,
In CS3, CS2, and OH, CS2
yes.
having quadrate, sir. Can you explain more?
In which pure alcohol or impure alcohol?
Pure, sir, pure. No, sorry, sir,
Pure
impure.
alcohol,
Not pure, sir, impure.
impure alcohol quartet only, no?
Quadrate. How,
How
sir?
it is quartet? CS3, CS2 proton, it is quartet only.
Sir, that I'm
CS3,
not
it gives
getting.
a triplet. Triplet and quartet. I told triplet and quartet, no?
Okay, sir.
Here, I will show you again. Okay. See, CS3, CS2,
Ji, sir.
and O. Because there is no proton. Yeah, this proton will be exchanged with the impurity here. Okay.
Okay, okay.
So there is no attachment of the proton. So
That will be
it
shift
gives
in
only two
action.
signals. This C, right, CS3 proton. So there are neighboring adjacent. There are two non-equivalent protons are there. So you get the 2 plus 1. It is triplets. And for this CS2 proton, there are three neighboring protons. So it is 3 plus 1 quartet only. Okay,
Yes, sir.
it gives a quartet. So the spectra appears triplet here and quartet.
Sir.
So this kind of graph, this kind of spectra will be appears.
All right, sir.
Okay,
Thank you, sir.
so the intensity. Yeah, these two intensities same, these two intensities same, and these two intensities same. This is some higher height than this one. Okay, so this is the difference. Okay, so in anywhere you go for interview or in for anywhere, so maximum they will ask first this question actually, right? In the faculty interviews or in the CSR interview or in anywhere, so they will question, right? So they will ask this question. So how many signals you will get for the pure alcohol and how many signals you will get for the impure alcohol? Right?
Mm.
So then you must differentiate these two alcohols and you must able to explain the reasons for getting the two signals for the impure alcohol and three signals for the impure alcohol. And if they ask why, what is the reason for this one, so you can go with this explanation here. And in the examination also many time it is repeated for the four marks. Okay, in the 4 marks questions, so they will ask many times this one. Okay,
Yes, sir.
so yes, so purity and impure alcohol is this one here. Yes, so here it is given that H1NMR spectrum of simplifying purified ethanol here. So here you can see here the triplet. You can triplet here is some pentate is there, right? So how we are getting this, you can see this. And this is the group, some important groups here, how can easily identify. So and you, I think you are very familiar with the multiplicity here. So it is not necessary to discuss this. Okay, for example, here, if ethyl group is there, okay, if ethyl group is there, so for CS2 proton, what will be the multiplicity here? CS2, it is quartet here, so you get quartet here. And for CS3, you get the triplets, right? And the ratio for the quartet, 1:3:3:1. And for triplet, so you get 1:2:1. So I think it is not, no need to discuss about this, right? And yeah, here also, for isopropyl kind of groups, okay. So for isopropyl kind of groups here, so how many signals we get? For example, here, CH and CSC here, right? So this kind of. So for this, actually, you will get two signals for this, right? These two methyl groups are falls in the same chemical environment. So you will get one signal for both methyl groups here, right? And for this particular CH protons, okay, this was CH group. So here you will get different signal. But when you are assigning the signal, when you are assigning the multiplicity for this CH protons here, okay, so you must consider the two groups as a neighboring protons here. These two, this one and this two. These two methyl groups should be considered as a neighboring protons here. So you take consideration of these three protons and three protons. There are 3 plus 3, 6 here, right? And 6 means n equal to 6. 6 plus 1, it is 7. So it is septate, right? So you will get this signal, this CH proton, that CH group will be gives a 7 lines, means 7 multiplicity here. Okay. And this will be gives a doublet only. So you can consider any one of this methyl or this methyl. So it gives a, then there is okay, the neighboring there are one proton is there, so it gives a doublet only. Okay. So all these are the examples it is given, right? So yes. So for example, if you see any, all these are the examples. So you can do the exercise of all these examples. So number of protons, yeah, number of sets of protons, number of signals. So here you remember the number of sets of protons, number of sets of proton equal to the number of signals here. Okay. Number of sets of protons, or the number of non-equivalent protons equal to number of signals here. For example, if you see in this example 3, okay. So this is so right. So the carboxylic acid here, phenylacetic acid. Okay, this is your phenylacetic acid here. Phenylacetic acid. So in the phenylacetic acid, if you see the how many signals appears here, you will get how many signals you will get here. So for benzene aromatic, you will get a multiplet here, and for this proton, you get one signal, right? This is A, this is B, and this is C. There are 3 signals. You will get the 3 signals here. For aromatic ring, you will get the multiplets, right? You will get the multiplets in the range of 6 to 8 generally. Okay, and okay, so and for this CS2 proton, right? This CS2 proton. So what will be the multiplicity for this? Actually, this is singlet one. Okay, because there is no neighboring proton. Because this side there is no neighboring proton, and this side also there is no neighboring proton. So this gives appears as a singlet here, and it will be falls in the chemical ship values of 3.53 here. Right. So actually it is a sp3. Okay, sp3ch proton actually. sp3ch. So generally the sp3ch proton, okay, the delta value, chemical shift value is, it is 0.92. Okay, 0.9 to 1.5 here. That is a range of, okay, sp3. Okay, sp3ch proton delta value is 0.9 to 1.5 actually. But here we are seeing the 3.53. 3.53 actually it is sp2 proton. sp2ch proton, it is ranging from 3.5 to 4.5 actually. 3.5 to 4.5. So actually this, as it is a sp3, right? It is a sp3, not sp2 here. It is sp3. Okay, being a sp3 proton, so it must appear set to in the range of below 1.5 actually. But we are seeing the appearance set to 3.53. More means it is appears in the shielded region, deshielded region here, downfield here, right? So in the downfield. So the reason is this particular proton is attached in between two electronegative groups here, electrophilic group. So where the benzene, aromatic benzene is electronegative group here, electronegative group here, and carbonyl also electronegative group here, CN, carbonyl as well as your aromatic. So this CH2 proton is it is located in between two electronegative groups here.
Victoria Memorial. తలుపులు ఎడమ వైపున తెరుచుకుంటాయి.
Right, so it is located in between two electronegative groups. That's why there is a drastic increase of there is a drastic increase of delta values takes place here. And one more proton like carboxylic acid proton, right? Carboxylic acid proton generally it appears in the range of 10 to 12, right? So it the range of this carboxylic acid proton is 10 to 12. And for aldehyde proton, the value is it is 9, right? So 9 to 10 here. So that is a range of the different protons here. And here for this carboxylic acid also, you can see the value is 11.95. Approximately it is 12. Okay, so it appears in the 12 delta value. So the reason is for where the hydrogen is directly attached with the more electronegative oxygen atom here, right? Where this oxygen atom, it is more electronegative atom here. And the adjacently it is there is a electrophilic carbonyl center is there. So due to this reason, okay, so it is directly attaching with this. So it is more influence with that electronegative atom. Okay, so with the electronegativity is directly proportional to the chemical shift values actually, right? Electronegativity is directly proportional to the delta. Delta nothing but chemical shift values here. Okay. So due to this reason, saying more so more increase of the delta values.
చైతన్యపురి తలుపులు ఎడమ వైపున తెరుచుకుంటాయి.
अगला स्टेशन चैतन्यपुरी, दरवाजे बाईं तरफ खुलेंगे.
Somebody is not getting mute. So you can see there are different types of compounds, graphs also given. You can see the one example we can see there is a 3-fluoropropionic acid, right? So 3-fluoropropionic acid. So how many signals you will get for this 3-fluoropropionic acid actually? So you can see there is 1, 2, 3. 3 signals is appears, right? So 3 signal is obtained for this propionic acid. For this A type of A set of protons, what is the multiplicity actually here? A set of proton, there are it is triplet, and for B set of proton again it is triplet here. Okay, because there is a CS2 proton neighboringly, so you can get the triplet for both set of protons, and for carboxylic acid proton you get the singlet. So that singlet is appears in the range of 12 here. You can see the here this is 12 in the range of 12 here. So this very small line, small signal is you can observe here. This is for your singlet for carboxylic acid. And so here we are getting the triplets and triplets. Okay. And you can see the coupling constant values, right? So you can differentiate this the coupling constant value. So you can see the where this particular J, okay, J2FH2. So here what they are showing the heteronuclear coupling for this 3-fluoropropionic acid. Right? So actually the homonuclear coupling is possible in the H1NMR spectra. And sometimes you can see the heteronuclear coupling also. Right? And there is some different technique is there to to activate that heteronuclear coupling. It is some different technique is there, and it is given some heteronuclear coupling with fluorine also. So in that case, okay, so we are getting this kind of multiplicity for this one, and the J value also given like it is 24, right? So for triplet, right? So here the doublet by triplets. So here the how it is given, right? Yes. So here doublet by triplet. Generally, the delta value is 2.80 here. You can see 2.80. It is in between 2 and 3, and J value is 24 here. Right? J value is 24 and 7. So here you see, so doublet of triplets. Okay, this doublet of triplet, and here also you can see the doublet of triplet in the range of 4 in between 4 and 5 here. Okay. So when we are considering the heteronuclear coupling, then we get this the possibility for having this doublet of triplet and triplet of doublet, whatever, right? But when we are considering the homonuclear couplings, we will get only 3 signals. One is triplet, 2 triplets, 1 singlet only. Okay. And yeah, so first order H1NMR spectra and second order H1NMR spectra is there. So they will differ with the J values here, whose value is higher. Higher values are first order, the lower values are second order, and weak interactions. So all these things aspects are there. So we discuss in the next class about the first order H1NMR spectra and the second order H1NMR spectra. So we discuss in the next class. So I'm stopping here.
Thank you, sir.